Hello everyone, welcome to Analog Electronic Circuits, lecture number 11. And today we are going to start with a new topic about cascode amplifier, or it is also called as common emitter, common base, directly coupled amplifier. So let us begin the analysis. So far we have done cascade, right? We have completed three types of cascade, which is common emitter, common emitter. Then there was common source, and the third category was common source, common emitter, right? And all were BJTs. I mean, the common emitter was BJT. CS was either JFET or MOSFET, and CE contained BJT as well as MOSFET. Now, in Cascode, we have around, common emitter, common base, or it is called as common source, common gate. So here it will involve BJT, and here it will involve MOSFETs, common source, common gate. So what's the basic difference between a cascode and a cascade? A cascade provides a very high voltage gain, whereas a cascode, but in a cascade, the limitation is the bandwidth, right? So over here, your AV is very, very high. So that's a good point. But the bandwidth is low, which is a very bad point. In case of Cascode, the voltage gain is not of concern, but the bandwidth is very, very high. And that's a very, very good point. Also, the current gain, AI, is also very, very high. And this voltage gain is moderate, same as your single stage amplifier. Okay. Also, one more difference between cascade and cascode is that in case of cascade, the stages are connected in series. Okay. Here we can write the stages are connected in series. Whereas in case of cascode, the two stages, let's say in this case, we are considering two stages. The stages are connected in parallel. Connected in parallel. Yeah. So that is the difference between your cascade and cascode, right? Later on, when unfortunately we don't have the high frequency response of a cascode amplifier, or else we would have proved this point that the bandwidth is very, very high, right? And it has different applications as compared to cascade amplifier. So we'll see that when we complete the MOSFET based common source, common gate cascode amplifier. After that, we'll see few applications where we can use a cascode amplifier instead of a cascade amplifier, right? So that was the quick difference between the cascade and cascode. Now let's continue back on a main topic, that is common emitter, common base, cascode amplifier, or a directly coupled amplifier. Now, what do you mean by directly coupled? That means the first stage output is connected to the next stage input directly without any RC coupling. So as you can see, the first stage output is collector 1 and the second stage input is emitter 1. So over here, there is no RC element present, direct connection is there. That's why it is called as a direct coupling. But in case of direct coupling, the first stage Q point might disturb the second stage Q point. I think not might, it will disturb the second stage Q point, right? So let us identify what is the first stage. So first stage over here, input is applied to the base and output is taken at the collector. So first stage is a common emitter stage. Whereas in the second stage, input is applied to the emitter and the output is taken from the collector. So second stage is a common base stage, right? And here we have a voltage divider, right? CC1 and CC2 are input and output coupling capacitors. CB is the blocking capacitor. And these somewhat arrangements have been made such that it works as a cascode amplifier, right? Now, other details about how this is working and what all things we have to find out. First of all, we have to focus on the DC analysis. So there are two alternate circuit structures. This is one circuit diagram for a cascode amplifier. So here it will work as an amplifier, but it will provide a very good bandwidth. It provides a very good current gain, which a cascaded amplifier cannot provide. And also your VS is a small signal AC signal. Your V out you get amplified AC, and VCC is required for the biasing the transistors in the proper forward active region for BJTs. Right now, there are two circuit diagrams, as I've already told you all. The same circuit which you see on your screens can be drawn as follows also. So this is the same circuit which you see on the screen, right? So if you trace back, let's trace back the Q2. So for Q2 at the base side, we have R2, R3, and above we have R1. So here it is. For Q2, above we have R1, and below we have R2 and R3. Also from the base 2, we have CB capacitor going to the ground. Yeah, base 2 we have CB capacitor going to the ground, with CB is the blocking capacitor, right? And also E2 is connected to C1. C1 is the collector terminal for Q1, and E2 is the emitter terminal for Q2. So yeah, as you can see over here, E2 is connected to C1. So as you can, similarly, you can trace back the entire circuit, and this is how it will look like. Now I will exactly tell you why we are having two circuit diagrams. So when we do the DC analysis, the circuit diagram in front of your screens will be utilized. And when we do the AC analysis, this circuit diagram which we see in front of your screens will be used. It will be utilized, right? In this case, where is the direct coupling? Well, the direct coupling is over here, from year to year. Okay. All right. So next, let us start with the DC analysis for the given amplifier, right? Also, one more thing, you note that what all things we can calculate from the AC analysis, right? From AC analysis, we have to calculate the input resistance. Let me write down what all things we have to find out. So first of all, we have to find out the Rn, then output resistance, then the voltage gain, and finally the current gain. So these four parameters we have to calculate from the AC analysis. And what all things we have to calculate with the DC analysis? So with the DC analysis, we have to calculate all the terminal currents and voltages. Terminal DC currents and voltages. This we have to find out with the DC analysis. Okay, so let us start with the DC analysis part. As I told you, the circuit diagram which you see in front of your screens will be used for the DC analysis of cascode stage. So let us start. So first part will be DC analysis. Let me switch to the, yeah. So first will be the DC analysis of cascode stage. Okay, and the configuration is common emitter, common base. All right, so let us begin with our analysis now. So as you know, in the DC analysis, all your capacitors will behave as open circuit. So all, we can just write connected capacitors there is a blocking capacitor, bypass will be open circuited. Okay, all the connected capacitors will be open circuited, and we will be left out with such a diagram. Let me draw it once and show it to you all. Yeah, so here is my Q2 and here is my Q1. Here we have RC, RE, then we have three biasing resistors R1, R2, and R3. All right. So here I'll connect to the base terminal of Q1. This is base terminal of Q2. This is Q1. And this is your supply voltage, VCC. This is R1, R2, R3, then this is RC and RE, right? So this is your DC analysis. Also, let me mention the terminal names. This is base 1, collector 1, emitter 1, base 2, collector 2, and emitter 2, right? Let me also mark the currents. So here we have IB2, here we have IB1, then we have current over here flowing through RC as IC2. This current is IE2, which is same as IC1. So IC1 and IE2 are same because they are the same point. And here this is IE1. So these are the various currents which are flowing. Now for the DC analysis, we will make one assumption. So what is that assumption which we will make? The assumption is as follows. We are assuming the base currents IB1, comma IB2 to be very small. To be very, very small. Their values are very, very small. So that will be in microamperes. Okay. So why we can make such an assumption? Now let us look back. So basically your emitter current in a BJT is equal to the collector current plus the base current. Now let me tell you the ranges of these things. So emitter current is normally in milliamperes. Collector current is also in milliamperes, and your base current is normally in microamperes, right? Which is 1,000 times smaller between milli and micro. So that's why normally we can assume that your IE is approximately equal to IC, right? Why approximately? Because if IE is 2.01 milliamperes, your IC value will be very close, pretty close. Let's say it is 2 milliamperes. That's why the emitter current and collector current are almost same. So using this assumption, we can completely ignore the current IB1 and IB2, and therefore the currents we can write as follows. So we can write IC2 is approximately equal to IE2, right? And IE2 and IC1 are same, which is equal to IC1, and IC1 is approximately equal to IE1. That means the current flowing, right, through this branch entire through the collector terminal C2 to the emitter 1 terminal, all the current flowing through this will be same. That means IC2 is same as IE2, which is same as IC1, which is same as IE1, which is very, very important, right? Many a time while solving numerical, people get confused in this. So at the start only, we are just making this very, very clear that all the collector current and the emitter current will be same in case of cascode amplifier, provided this assumption is there, right? All right. Next thing which we have to do is we need to calculate the voltage Vb1 and Vb2. So basically, let me mark the voltages over here. This is Vb1 across this node, and here it will be Vb2, right? So first of all, let us calculate Vb1. So for Vb1, we have considered that Ib1 and Ib2 are almost negligible. So let me redraw the network. Let me slightly go down. Let me redraw this for, this transistor. So I will draw for Q1 transistor. This is Q1. And let me draw this side. This is R1, R2, and R3. This is R3, R2, R1, right? And here we have current flowing, which is almost negligible, zero current flow, right? And it doesn't matter what we have connected at the top or bottom. You have to just concentrate over here. So this voltage over here, let me mark it as, this voltage over here is VB1, measured with respect to ground. It's a DC quantity, right? Now we can easily apply of voltage division rule provided this base current is almost zero. So what does the voltage division rule says? Vb1 will be equal to R3 divided by R1 plus R2 plus R3 into VCC, correct? So it will be Vb1 will be R3 divided by R1 plus R2 plus R3 into VCC. Okay, so that's the value of VB1. Now, next, what is the, VB1, VBE1 can be written as VB1 minus VE1. Normally, the value of VBE is, if it is not given, we take it as 0.7. And if it is given, it is normally 0.7 only, 0.6 to 0.7. From here, can we write VE1? We take this on this side is equal to VB1 minus VBE1. So from here we have calculated VB1 and we have calculated VE1, right? Because your VBE is known. This is known value. Okay, so we can easily calculate the value of VE1. Now next, we will calculate the value of VB2. So for that also we'll draw a separate diagram, and let us draw it over here. So let us say this is my transistor Q2, right? I'm not interested in what is connected at the collector and the emitter. I'm more interested in what is collected at the base terminal. So here we have two resistances. Over here, this is going to the ground, and over here we have base 2, VB2. This is VCC, R1, R2, R3, and this is over here we measure VB1. All right, measured with respect to ground, of course, and it's a DC quantity. Now, again, the current flowing over here in the base terminal is almost negligible. So how can we write this VB1 now? So VB1 will be R2 plus R3 divided by total resistance R1 plus R2 plus R3 into VCC, right? So over here, actually this should be first thing which we did. This is VB2 actually. Sorry for that. Because above terminal is base 2, so this will be VB2. So VB2 will be R2 plus R3 divided by R1 plus R2 plus R3, right? So let me rewrite this as VB2 is equal to R2 plus R3 divided by R1 plus R2 plus R3 into VCC, right? So that's the value of VB2. Now, similar manner, we can also calculate VE2, right? So what will be VE2? VBE2 is given by VB2 minus VE2. So over here we can write VE2 is equal to VB2 minus VBE2, right? Normally your VBE voltage is known, so this quantity is known. So if we know the value of VB2, we can easily calculate the value of VE2, right? So these are the terminal voltages. Now, what about your okay, once we know the value of VE2, now look at this diagram carefully. Your emitter 2 and collector 1 are at the same point, right? So once we know the value of VE2, we can easily calculate VC1, right? So how can we? So let us see. So one VE2 is same as VC1, right? As you can see from this diagram. Now only terminal voltage left is VC2, right? So for VC2, let me draw this Q2 transistor carefully, and let me draw VCC, RC, and that's it. So let me redraw it over here. So I'll use a red color I'll use a black color to draw that now. So this is my Q2 transistor. I have connected RC resistance. Here I have VCC, right? And I want to measure VC2. This is again with respect to ground, Vc2. Now we know that the base current over here is 0, so that will hardly matter. And here the current flowing over here is IC. So what is the value of Vc2 over here? Can anyone tell me? Vc2. So Vc2 will be Vcc minus ICRC, right? Your Vc2 will be Vcc minus IC into RC, right? So all the terminal voltages expressions are found out over here, right? So let me write in summary what are the terminal voltages which we can have to calculate if we are given a cascode amplifier. So what are the terminal voltages which we are interested in? We are interested in Vb1, Vc1, Ve1 for Q1 transistor and Vb2, Vc2 and Ve2, right? And what are the terminal currents? Terminal currents in this DC analysis will be IB1, IB2. This is treated as 0 because they are assumed to be very, very negligible. Then we have IC1, right? Then we have IC2, IE1 and IE2. So in the terminal currents, it's very straightforward. Base currents are almost 0 and rest all the currents are same, right? So finding terminal currents is very, very simple. But terminal voltages, you'll have to use different expressions to find each of them. So these are the terminal voltages and terminal currents for the cascode amplifier under DC analysis. All right. Now, next we move on to the AC analysis, right? So let me move over here slightly. AC analysis, second part. Let me start from here itself. Okay. I'll use a black color. So we'll write AC analysis of cascode stage. AC analysis of cascode stage. And what is the cascode amplifier which we are talking about? Common emitter, common base, right? So let us begin with the analysis now shortly. So as I've told you all before, for the AC analysis, we will be using the circuit diagram which is given over here. So what I will do is I'll cut and copy this circuit diagram from here and paste it at the required location. Just give me a second. So let me first select it. And I'll copy the entire thing so that I don't have to do that again. Just this is for the explanation part. You all can just have a look at it. You all will be drawing the mid-frequency AC equivalent circuit. Okay. So for the AC analysis, let me add, yeah, that is added very easily. So for the AC analysis, what are the conditions to be followed? For the AC analysis, we need to short circuit. We need to short circuit DC supply or DC source and all connected capacitors. We need to short circuit DC source and all connected capacitors. Okay, and that is what we will be doing it over here right now in live. Okay, fine. So let us begin. So first of all, we'll replace all the capacitors with a short. So let me just do that quickly. All the coupling capacitors and the blocking capacitor will be replaced by a short. So let me do that. I'll use a blue color. Okay, this is a short. This is also a short, whereas this is also, yeah. So all the capacitors are connected as a short circuit. And now VCC also it's grounded. So VCC is also short circuited. So over here, this will be grounded and also this will be grounded. So let me add that ground over here. Okay, so the circuit has become extremely simple now. So here a resistor is there. In parallel, we have a short. So resistor will disappear, because if we have a resistor in parallel with a resistance, if we have a short in parallel with a resistance, there is this resistance will become redundant. Okay. Also, let us see one more thing over here. See this base terminal, your base 2 terminal is grounded, right? And this terminal is connected over here. So that means this terminal is grounded, right? This is the base 2 which is going over here, right? This also becomes base 2. So that's the same terminal, right? Base 2 is grounded. So that means your R1 resistance also becomes redundant. Okay. Your R1 resistance also becomes redundant, and that is gone, right? So R1 is also gone. And then we have R2 in parallel to R3. So R1 and R2 will be in parallel, right? So if I can redraw the circuit again, let me do that. Okay, let me just slightly reduce it. What I do is I'll copy the circuit again. There are some changes which I have to do, so that simplified form, it will be in a simplified form. Let me push it slightly up above. Yeah. And let me make a copy of it. Okay, just a second. It will eventually work. Yeah. Yeah, let me take a copy of the circuit so that I will draw the modified circuit, simplified circuit in that sense. Okay, I have copied it. Now let me move slightly down. So around here, I will be adding that circuit now. Yeah, it has slightly moved down. So I'll shift it up slightly. Very excuse for this slight delay, because we are moving step by step. So let me move on a little this side. Yeah. So yeah, we are ready to resume now. So once we have simplified the network, our circuit will reduce to something like this. Let me maximize this now. Okay. So this base terminal is grounded, that is gone. So this wire has no meaning at all. So let me delete this wire. Base 2 terminal is grounded. So this is gone. This resistor R1 becomes redundant. This R1 and R3, I will make it parallel. I'll connect them in parallel. Just wait a minute. Yeah. I'll write over here, instead of okay. Let me redo it. Let me disconnect this wire, because this is redundant. R1 resistance is not required. And let me replace that. This is R2 parallel to R3. Join the connections back. Yeah. So this is the simplified form, and this is your RC coupling. I mean, direct coupling, sorry. Yeah. So that is what we were looking for earlier. Earlier, what did we have? We have R1 redundant. So we removed it from here, and R2 and R3 we have connected in parallel, right? And that parallel resistance, we can call it as RB. So RB will be R2 parallel to R3. So this is your modified circuit which we were looking for. And also for simplicity, this R3, RC is connected above, will connect it below. Let me just use a eraser. So instead of connecting at the top, we will be connecting it at the bottom over here. So this is the simplified AC analysis, AC equivalent circuit. And next, what we will be doing is we will be drawing a mid-frequency small signal equivalent circuit. So let us start with the analysis. So let me write it down. Mid-frequency. So what is the difference over here now with the AC analysis, AC equivalent circuit and mid-frequency? So in mid-frequency small signal equivalent circuit, your Q1 and Q2 will be replaced by Q1 and Q2 transistor will be replaced by its hybrid pi model. So it is mid frequency small signal equivalent circuit. Okay. So now let us continue with our analysis. Mid frequency small signal equivalent circuit. So over here we will be replacing transistor Q1 and Q2. We will be replacing transistor Q1 and Q2 with its small signal hybrid pi model. Now replacing transistor Q1 is not an issue because it is in a standard form, base, collector and emitter. That is how we should be doing. So let me draw that quickly. Okay, let me use a black color and start with this is base, collector and emitter. Let me mark over here base 1, collector 1, and here we have emitter 1. So between base and emitter, we always have R pi. We call it as R pi 1 because we'll be having R pi 2 also. And this voltage we can call it as V pi 1. And over here we will have a current source, a voltage dependent current source, which we can call it as GM1 times R pi 1. And we are ignoring the RO over here right now for this analysis, right? So this is my small signal hybrid pi model for Q1 transistor, right? There is no problem in it. But for Q2 transistor, the orientation is different, right? It is like 90 degrees rotated on the clockwise direction. So we have emitter 2 above on the left hand side, base is below, and collector is at the right hand side, right? So we have to draw the model also. We have to orient it in this manner, right? So let me draw that way a short model over here, small signal hybrid pi model. So here we have base 2, here we have emitter 2, and here we have collector 2. So we have to remember the basic thing, right? So what is connected between base and let me use a black color. So what is connected between base and emitter? R pi, right? So here also we'll have R pi 2. But the positive and negative sign will be directed like this. It is directed from base to emitter. So this is V pi 2, right? What is between collector and base? Nothing. It's open circuit. And what is connected between collector and emitter? Between collector and emitter, we will have a current source directed from collector to emitter, right? Like this. So this current source is GM2 into V pi 2, right? Yeah, so that's it. This is the connection. So this same small signal hybrid pi model for Q2, we have to do it down. We have to add over here, right? So, so let us begin now. So over here, let me add that small signal model for Q2. So first of all, here we will have emitter, and here we will have base, and over here we will have a collector. So let me mark over here. This is emitter 2, base 2, and collector 2. Again, I repeat, between base and emitter, we will have R pi. We call it as R pi 2, but the voltage polarity will be reversed because it's going starting from base towards emitter. So V pi 2. Collector and base are open circuited. And what is connected between collector and emitter? Collector and emitter, we have a current source. So here is the current source directed from collector to emitter. So this we can call it as GM2 into V pi 2, right? So yeah, these are the connections which we have made. Now we have to see what all things are connected to each terminal now. So let's go back to the circuit diagram. Here it is. So to the base one, we have R2 parallel to R3, right? We can call it RB also. And we have in parallel voltage source Vs. So let us do that. Or it is V in or Vs. Let me cross check it once. Yeah, we are calling it V in actually. So everywhere we should follow the same syntax. Let me change this as V in only. Okay. Let me use the eraser and call it as V in everywhere, because we should follow one common this thing. notation. We again call over here, call this as V in instead of Vs. And here also I'll be calling it as V in. Let me do the changes everywhere so that there is no confusion later when you refer the handout. Yeah, this is V in. So I will have a V in voltage source in parallel with RB, right? So let me draw that. So here I will have a voltage source named as V in, and then I will have a resistor named as RB, which is R2 parallel to R3, correct? So this will be R2 parallel to R3. Now let's check what is at the emitter 1. So from here, straight away from the AC equivalent circuit, emitter is grounded. So let's ground the emitter 1 terminal. So emitter 1 terminal is grounded. Now, collector 1 and emitter 2, let's see now what is connected. Directly connected. No other thing is connected. Directly, collector 1 and emitter 2 are tied together. So let us do that over here also. So instead, what I will do is I will push this slightly on the left hand side so that we save some space, and equivalent circuit looks more compact. Yeah, it is done. So now let us connect collector 1 and emitter 2 as it is without anything over here. Now let us check what is connected at the base 2. So base 2 is directly going to the ground, right? So that is also we will be connecting it to the ground. So here it is. Base 2 is connected to the ground. And from collector 2, what do we have? From collector 2, we have RC, and in parallel, we have V out marked, right? So here we will mark RC, resistance RC, and in parallel to that, we'll mark V out. So here it is V out, correct? So our mid frequency small signal AC equivalent circuit is complete now. Fine. All right. Okay, fine. So now we need to find Rn, we need to find R out, and we need to find a voltage gain. So let us start by defining the voltages. So in between, the output of the first stage was called as V out 1. So we'll be calling this as V out 1 only. So V out 1 is the output of the first stage applied as the input to the second stage, and V out is the output of the second stage, right? So let us first calculate. Let me mark over here R in input resistance. So input resistance is, let me mark over here. Input resistance is looking at the base terminal. This is R in. So what do you see R in? RB, which is R2 parallel to R3. And again, we have a resistor R pi 1. So it is RB parallel to R pi 1, right? So that is my R in, straightforward from the mid frequency small signal equivalent circuit. We have Rn is equal to Rb parallel to R pi 1. If you want to write it down in more details, it will be R2 parallel to R3 parallel to R pi 1. So that's the expression for R in, input resistance. Now let's calculate R out on the similar lines. So R out will be looking at the output terminals over here. Let me use orange color. Yeah, this is R out. So looking over here to the left hand side, what do you see? You see RC, register RC. The impedance offered by the current source will be infinite, right? So that RC only will be remaining. So over here, we will have R out equal to RC. Very easy, straightforward, right? So the output resistance of a cascade amplifier is same as the output resistance in case of a single stage amplifier, right? Now we have to calculate the voltage gain, right? So next we have to calculate the voltage gain. Okay, so next we have to calculate the voltage gain. So let me add over here. the overall voltage gain will be the product of the individual stage voltage gain. So first of all, let me write the formula. It will be V out upon V in, which can be written as V out upon V out 1 into V out 1 divided by V in. Now let us check it out what these terms mean. So the first term expression over here, that is V out upon V out 1, is the gain of the second stage. And V out 1 upon V in is the gain of the first stage, right? So we need to find out the values of AV1, the gain of the second stage, and AV2, and multiply them to find out the overall voltage gain. Now let us begin. So let us go back to the circuit over here. Now, what is the value of V out, right? Let me use a different color, orange color. So what is the value of V out? How can we write V out expression? So V out can be written as this current over here. Can we call this current as IC2? Yes, this current is IC2. So that's the outgoing current not going towards the ground. So we can write V out is equal to minus IC2, this current into the resistance RC, right? So we can write V out is equal to minus IC2 into RC. All right. And what is your, value of IC2? IC2 is nothing but GM2 into V pi 2. IC2 is GM2 into V pi 2. And what is V pi 2? V pi 2 is nothing but minus of V out 1. As you can see, this V out is plus minus over here, and this V pi 2 is plus minus like this. So V pi 2 is in parallel with, you know, V out 1, but with the opposite polarity. So V out, V pi 2 is nothing but minus V out 1. Now let us write that systematically somewhere else over here. Okay, so we'll write it systematically over here. We are finding the gain AV2. So first of all, we found out that V out is equal to minus IC2 into RC. That is, V out is equal to IC2 is what? Minus GM2 into V pi 2 into RC. And from here, we found out that V pi 2 is nothing but minus V out 1, right? So how can we write the above expression now? V out 1 is equal to minus minus will get cancelled. You'll get GM2 into V out 1 into RC, right? So we can write V out upon V out 1, which is nothing but AV2, which is V out upon V out 1 is equal to plus GM2 into RC, right? So that's the expression of the gain of the second stage. This is the expression of the gain of the second stage. So let me write it down over here. Yeah, let me use a black color. This is the gain of second stage. All right. So we found out the gain for the second stage. Now let us concentrate and find the gain for the first stage. Okay. So now, similarly, we have to write down what is the expression for V out 1, right? We have to write down the expression for V out 1. Now, over here, V out 1. So what is the current flowing over here? Basically, what is the current flowing over here? In case if you want to multiply V out 1, let me write over here, your collector current, okay, this is collector current IC1, which is equal to emitter current IE2. All right. Now, how can I write this expression now? V out 1. So what is V out 1? What is V out 1? Anyone? It will be IE2 into R pi. it will be IE1 into R pi, because this current over here is IB2. And we know that IE is basically IC plus IB. So here, as you can see, there are two incoming currents and outgoing current is IE2. So IE2 into R pi 2 will be your V out 1, right? So we can write over here minus IE2. Can we write IE2 over here? Or it will be, IB2 into R pi 2. What it will be? Now, how to convert IB2 into IE2? We know that the expression IE is basically, this will be 1 plus beta times into IB, correct? IC is beta IB, right? So IE will be 1 plus beta times IB, right? So how can we write IB in terms of IE? It will be, IB will be equal to IC, sorry, it will be IE divided by 1 plus beta. So if I want to convert this into emitter current, right, it has to be divided by 1 plus beta 2, because it is of the second stage. Are you all following? Again, I repeat, your V out 1 is nothing but IB2 into, V out 1 is actually opposite of V pi 2. And what is V pi 2? First of all, let me write what is V pi 2. V pi 2 is plus IB2 into R pi 2. Okay. V pi 2 is nothing but IB2 into, let me add it in the same format, IB2 into R pi 2. But V pi 2 and V out 1 are opposite polarity. So if V pi 2 is IB2 into R pi 2, V out 1 will be minus IB2 into R pi 2. Correct? Now let me write it in a formal agreement over here, that this is your AV1. And what did we found out so far? That V out 1 is equal to minus IB2 into R pi 2. Correct? Now we have to convert this into emitter current, right? So when we convert this into emitter current, how can we write the same expression? That is V out 1 is equal to minus of IE2 into R pi 2 divided by 1 plus beta 2. What we did, we replaced IB by IE. And in doing so, we have divided by 1 plus beta. All right. Any doubts over here? Okay. Now, what is this, emitter current and collector current is actually equal to this IE2 is basically IC1, correct? So what is IC1? GM1 into R pi 1. So let me write over here further that IE2 is same as IC1. And what is IC1? IC1 is GM1 into R pi 1, right? And GM1 into V pi 1. Sorry for that. Sorry, very sorry. This is GM into V pi 1. GM into V pi 1, right? IC1 is GM1 into V pi 1. And what is V pi 1? V pi 1 is same as V in. As you can see, they are in parallel. V pi 1 is same as V in. So we'll write this as IC1, which is equal to GM1 into V pi 1. And your V pi 1 is nothing but V in. So finally, we can write the output expression as follows. V out 1 will be equal to minus of, instead of, IE2, we'll write GM into V in into, I think it will be GM1 into V in. It will be R pi 2 divided by 1 plus beta 2, right? So finally, we can write it down as, AV1 is V out 1 upon V in. So we can write this as follows. That is AV1, which is V out 1 divided by V in, is equal to minus of GM1 into R pi 2 divided by 1 plus beta 2, right? So that's the exact expression for AV1, right? Let me just, this is the exact expression for AV1. But we can approximate this further. So let me do that. So basically your 1 plus beta is normally, approximately equal to beta itself, right? Your beta value is very, very large. Beta 2 is very, very greater than 1. So 1 plus beta is approximately equal to beta 2 itself. So let me rewrite this. AV1 is minus of GM1 into R pi 2 divided by 1 plus, sorry, not 1 plus, divided by beta 2. Okay. So that is what it stands. Now, assuming both the transistors, assuming both Q1 and Q2 are symmetric, assuming both Q1 and Q2 are symmetric. What does that mean if they are symmetric? If they are symmetric, then we can write GM1 will be equal to GM2 and R pi 1 will be approximately equal to R pi 2. So we can do the following changes in the same expression. So we can write that is AV1 can be written as AV1 can be approximately written as follows. It will be GM2 instead of GM1 we can write GM2 into R pi 2 divided by beta 2. Now one more thing is there. What is GM? GM2 can be written as IC2 divided by VT, right? And what is R pi 2? R pi 2 is beta VT upon IC2. So this is beta, actually this would be beta 2, right? Yeah. Now if we somehow multiply GM2 into R pi 2, what do we get? So GM2 into R pi 2 will be equal to IC2 upon VT into beta 2 VT upon IC2. So over here IC2 gets cancelled out, right? And VT also gets cancelled out like this. So what is left? We can easily write over here GM into R pi is same as beta 2, correct? So this we substituted over here. So instead of having GM into R pi 2, we can replace it by beta. And where did we get this from? We got it from over here. Okay. Now, finally, we can write the expression as follows. But this is an approximation. Huh? This I should have used the approximation sign from the start itself. This is approximately equal to. So it is minus beta 2 divided by beta 2, right? So that is AV1 is approximately equal to minus 1, right? So AV1 is my gain of my first stage, and my first stage is a common emitter stage, right? So this is the gain of first stage for the cascode amplifier, right? And now when we know, the moment we know the gain of the first stage and the second stage, what will be the overall voltage gain now? Let me come back over here. So now if we want to calculate the overall voltage gain, it will be AV2 into AV1, and AV2 value is I think I think plus GM2 into RC, and AV1 value is minus 1. So we can write over here safely minus GM2 into RC is the value of the overall voltage gain for a cascode amplifier. So this is for common emitter, common base, cascode stage. This is the overall voltage gain for common emitter, common base, cascode stage. So this is how we calculate the overall voltage gain. Sometimes we write it as AVT, that is the overall voltage, total voltage gain, or overall voltage gain we can write it as AV. So that's how we can derive the expression for the voltage gain for a cascode amplifier. Fine. If you all have any doubts, you all can ask. All right. So next we have to find the current gain. So for current gain, I will require this mid-frequency small single equivalent circuit again. So let me make another copy of it. So let me add that as it is. Give me a moment. It will be done within a few seconds. Let me add it below because we are going to find now next the current gain. So for current gain, we should represent all the quantities in terms of current from input to output. So let me go down over here. Okay. So let me add over here itself, right? Let me see where I can add the data. Yeah, here itself. So now we are finding the current gain, right? So let me rub out the quantities which are not required right now. Okay, so here it is not required. So what are we finding? We are finding the current gain. Current gain denoted by AI. Yeah. Current gain for a cascade amplifier will consider the same mid-frequency small signal equivalent circuit, but with slight modifications. Everywhere will mark the current levels. Okay. So let me begin. Also, let me just rub out the R in and R out, because that is not the aim over here right now. Okay, let me start from here. So here we call this current as, let me use orange color for marking the currents. Here it is called as I out. I out. So this is collector current, this is base current, this is emitter current, that is fine. This collector current, this will be IB1, all right. And this current over here will be I in. Fine, so we have marked the various currents. Now what will be a current gain? Similarly, what will be a current gain as we have found out the voltage gain? So a current gain AI will be the output current I out, the output current I out divided by the input current I in. All right. And this we can find out, very patiently over here like this. So we can write it as AI is equal to I out. We cannot directly find it. We'll find it step by step. So it will be I out divided by IC2 first. I out divided by IC2 multiplied by IC2 divided by IB2. IC2 upon IB2. Then we have IB2 upon IC2. IB2 upon IE2, sorry. Then we have IE2 upon IC1, IE2 upon IC1. Then we have IC1 upon IB1, IC1 upon IB1. And finally, we have IB1. Here it is. This is the base current, right? This is IB1 divided by I in. So it will be IB1 divided by I in. If you look carefully, you will get back the original expression I out upon I in only, right? So we have to find this intermediate current everywhere. So let us denote this as some terms, quantities. So let me denote this as 1. This is 2, 3, 4, 5, and 6. And let us find them one by one. So first of all, what is your output current I out and IC2 relation, right? So let me add over here orange color. So I out, if you look carefully, I out and IC2 are one and the same thing. Okay. So I out divided by IC2 will be equal to 1. Okay. I out upon IC2 will be equal to 1. And that was the first expression over here. So first is over. Okay. Next is IC2 divided by IB2. Okay. So IC2 divided by IB2, it's very simple. IC2 is beta times IB2. So your result will be beta 2 only. So this is the second expression over here. Then next is what is the relation between IB2 and IE2? Okay. What is the relation between IB2 and IE2? So let me add the third point over here. IB2 and IE2. So the relation is as follows. It is IB2 and divided by, here it is 1 plus beta 2 times IB2. So what is left out? 1 upon 1 plus beta 2. So third term is also very clear. Now next is IE2 divided by IC1. Okay. IE2 and IC1, if you see carefully, they are one and the same. So the fourth term over here, IE2 is equal to IC1. So IE2 divided by IC1 is equal to 1. So the fourth term is also very, very clear. Then comes the fifth term. So in the fifth term, we have IC1 divided by IB1. This is also very straightforward. IC1 is beta times IB. So beta 1 into IB1 divided by IB1. So finally, you will have over here beta 1 itself, right? Now we have to find out the sixth term, IB1 and IN. So for finding that, we will be having a current division rule. We will be drawing the circuit again, this part. So here we have IN, right? We have RB, and then we have R pi 1. R pi 1, we have IB1 flowing, and here we have IN, right? So let me redraw the circuit over here quietly. So we have a situation which looks something like this. So this is RB, and over here we have R pi 1. This both the resistors are grounded. The current flowing over here is IB1, and the current flowing over here is IN. So we can use current division rule. So by current division rule, or we can call it CDR, what is the value of IB1? So IB1 will be other resistance, right? Other resistance is RB divided by RB plus R pi 1 into the source current, which is IN. So what is the value of IB1 upon IN? So that is what the sixth expression means. So IB1 divided by IN is nothing but RB divided by RB plus R pi 1. Okay. So now we have only thing left is to substitute all the equations or all the expressions in this AI again and find out the overall expression of the current gain. So let us do that. Let me add over here only. Okay. Just a minute. Yeah. So here, let me rewrite the expression of AI here once again. So AI will be equal to first term. So what is the first term over here? First term is 1, right? Let me do one thing. Let me rewrite this entire expression again. Okay. Just for simplicity, so that everything will fall in place. Okay, fine. So here it should be I, and here it should be IN. Let me rewrite this. This should be IB1. Yeah, all right. So, and this, let me take it a little down. This will be the current gain. Okay, sorry for the delay. This is AI equal to. So what is the first term over here? We have. So for the first term, we have 1. So 1 multiplied by. The second term will have beta 2. The third term will have 1 upon 1 plus beta 2. Now 1 plus beta 2 can be approximated as beta 2 itself, because the value of beta 2 is very, very large, right? So this we can take into account and write over here 1 upon beta 2. Sorry for that. Yeah. Next is IE2 upon IC2. They are 1, right? They are same. Actually, we have seen that. This will be beta 1. And finally, we will have RB divided by RB plus R phi 1. Let me write it properly as RB. Yeah. And we know that the transistor Q1 and Q2 are similar. So Q1 and Q2 have similar parameters. Have similar parameters. So what do you mean by having similar parameters? Beta 1 is equal to beta 2 is equal to beta, and R pi 1 is equal to R pi 2 is equal to R pi, right? So in the above expression, what are the terms which are getting cancelled? Beta 2 and beta 2 is getting cancelled. And so we can write AI, we can easily write AI will be equal to, or we can write approximately equal to, because we have made an approximation over here, will be approximately equal to beta times RB upon RB plus R pi. Fine. So this is the expression for AI, which can be written as follows. Now we know that beta is nothing but Gm into R pi. We can also write in that terms. So, I mean, this is also the expression is correct. This is absolutely fine. And this is the current gain expression for current gain of common emitter, common base, cascode states. Okay. Or we can also write it as AI is approximately equal to Gm into R pi into RB upon RB plus R pi. It's just an alternate form. Both the above expressions are one and the same only, right? So this is how we calculate the current gain for a cascode amplifier, right? So cascode amplifier advantage is it provides you a high current gain in comparison to a cascaded amplifier, right? So yeah, it was a long analysis and the current derivation. I hope that current gain, how we got the expression, it is very, very clear. If not, you all can rewind the video and have a look at it once more. I'll recommend that you all practice this in your book so that you for better clarity, right? And yeah, so we started. Let me revise what we did so far for the analysis of cascode amplifier. Yeah, let me go back to the initial one. Okay. So for the cascode amplifier, that is common emitter, common base, directly coupled cascode amplifier, we first found out the DC analysis, all the terminal voltages and terminal currents. Then we did the AC analysis to find the input resistance, output resistance, the overall voltage gain, and the overall current gain for the given cascode amplifier. And that will be all for today. Next time, we will be solving a numerical on cascode amplifier, right? On the same concept. So that's all for today. Thank you everyone for joining. See you next time.